All right, let's talk about uranium. It's got this wild split personality. On one hand, it's this incredible source of power, right? But on the other, it's this notoriously dangerous waste. It's the ultimate double-edged sword. So that's the big question we're tackling today. I mean, how can one single element be both? How can it be a world-changing fuel and a million-year waste problem? It sounds like a total paradox, doesn't it? Well, the secret, it's hiding deep, deep inside the atom itself. So yeah, let's get into it. Okay, so our first stop, a tale of two atoms. And this is where it gets really interesting because the tiny difference we're talking about, it changes everything. Seriously, you have these two atoms that are almost perfect twins, but one tiny little detail makes all the difference in the world. So to really get this, we have to talk about something called an isotope. Now, don't let the sciencey word throw you. It's actually a pretty simple idea. Think of it this way. The number of protons is like an element's ID card. If an atom has 92 protons, it's uranium. No exceptions. But it can have a different number of neutrons, and that's what creates these different flavors or isotopes of the exact same element. And here it is, laid out plain and simple. We've got our two isotopes, uranium-235 and uranium-238. Now look at the protons. See, both have 92. That's what makes them both uranium. But then you look at the neutrons, and that's where things get different. U-235 has 143, but U-238 has 146. 3. That's it. Just 3 tiny little neutrons. I mean, think about that. The entire massive difference between the fuel that can power a city and the waste that we have to bury for a million years, it all comes down to just 3 neutrons. It's kind of mind-blowing when you think about it, right? A number that small having such world-changing consequences. All right, next up, the fissile difference, or why one of these atoms splits and the other one doesn't. So yeah, how does a tiny difference of 3 neutrons lead to such a huge difference in what they do? Well, it all boils down to one critical property called fissility, and this, my friends, is what separates the powerhouse from the dud. So let's break down that word fissile. What does it actually mean? Well, a fissile material, and this is our U-235, is really special. When a neutron smacks into it, it doesn't just, stick. Instead, the whole atom gets super unstable and literally splits in two. And that split, that fission, unleashes a crazy amount of energy. But, and this is key, it also releases more neutrons. And those extra neutrons are what create this incredible chain reaction. It's like a domino effect on an atomic scale. So look here, a single neutron hits a U-235 atom. Boom, it splits. It releases a ton of energy, and crucially, it kicks out a couple more neutrons. Now those new neutrons go on to hit other U-235 atoms. And what happens? Boom, they split too, releasing even more energy and more neutrons. It just keeps going and going, this self-sustaining reaction. That's the engine of a nuclear power plant, and also a nuclear bomb. But what about its big brother, uranium-238? Well, those 3 extra neutrons act like atomic glue. They make it way more stable. So when a neutron hits it, it usually just swallows it whole. No split, no big energy release, no new neutrons to continue the chain. It's basically the dud in the firework factory. Now, don't get me wrong, it's still radioactive and you definitely don't want to mess with it, but it just doesn't have that game-changing ability to create a chain reaction. Okay, so this brings us to the real world and a huge challenge, the high cost of enrichment. We're talking about separating the useful from the, useless, because out in nature, the useful U-235 and the much, much more common U-238 are all mixed together. And to get the fuel we need, we have to pull them apart. This process is called enrichment, and believe me, it comes at a staggering cost. And this chart, wow, it really shows you just how big that challenge is. When you pull uranium ore out of the earth, a staggering 99.3% of it is that stable U-238, the stuff that becomes waste. And the fissile, useful U-235 that we need for fuel, it's that tiny little sliver right there, less than 1%, just 0.7%. That's it. So just let that sink in for a second. To get that tiny, tiny sliver of fuel, we have to process a whole mountain of ore. It means the primary product of uranium enrichment isn't actually fuel, it's waste. For every little bit of useful fuel you manage to create, you're left with a huge amount of this depleted uranium, which is basically just that U-238 left behind. So let's pull all this together. Why does this all matter? Well, for one, the fuel we need, U-235, is insanely rare. And the leftover stuff, U-238, is overwhelmingly common. Number two, separating these two things that are almost identical is a massive, massive industrial challenge. And finally, and this is the really important part, this whole process, it has very real consequences for our world, for specific places and the people who live there. And that brings us to this powerful final thought from the source material we've been looking at. Quote, "The demand for U-235 turned this land into a Cold War extraction zone." Just think about that. A simple difference of 3 neutrons in an atom you can't even see was enough to create these huge geopolitical forces that literally reshaped the land and people's lives. This whole split between fuel and waste isn't just some neat science fact. It's a story that's been carved into the earth. And it leaves us with a pretty heavy question, doesn't it? What is the real cost of pulling these two atoms apart?